So in this unit, we are looking at this whole idea behind evolution. Remember, evolution is just this concept that things have changed over time. And it all comes down to mutations. Remember, creatures are just randomly born with mutations, and nature's going to say, let's see what happens. So creatures don't know what color they are. Like a rabbit doesn't know what color it is. A walking stick bug doesn't know it looks like a tree limb. There's some types of crickets that look like leaves. They don't know what they look like. These creatures just happen to be born with a mutation, and that mutation gave them certain characteristics. And because of where they live, they can hide, they can camouflage and not be found, and they don't get eaten. So when we look at evolution, we are looking at this idea that things have changed over time. And the most common example is due to mutations. Well, we always look for evidence of evolution. And you guys know the number one piece of evidence for evolution is fossils. We know that all of your life, kids have been fascinated with fossils, particularly dinosaurs, because dinosaurs are these really big creatures that are no longer around, they're extinct. But what is a fossil? Basically, a fossil is any evidence of a dead organism. It doesn't have to be bone, but like you see in this picture, leaves. Leaves don't have bones. But as a leaf falls to the ground and it gets covered with sediment, and over time that sediment gets pressed and gets harder and harder and harder and turns into a rock. But as the leaf biodegrades, the chemicals in the leaf, the pigments in the leaf, remember pigments are inks, they can leave a pattern. So this pattern of a leaf on this rock would count as a fossil. You can have animals stuck in amber. Amber, as you know, is basically a jewel made from tree sap. Well, there used to be some really big trees that made a lot of sap. And so it's possible to trap animals in it. Most of the time when we find a fossil, though, you're not really finding bones. You're finding like an imprint, because over time, the creatures will biodegrade. So we will have this imprint like a footprint. But also over time, as the creatures biodegrade, other minerals can get inside of that, basically that mold that they left behind, and form kind of like plaster casts or kind of like statues that show us what they used to be like. But fossils aren't always going to be bones. And so with fossils, as you know, this is what we use as our number one source of evidence for evolution, because we have this thing called the fossil record. Now, the fossil record is not perfect. There are some areas in the world where we don't find fossils. For example, the tropical rainforest. It's very hard to find a fossil in a tropical rainforest because it's so humid there that creatures biodegrade very quickly. And so they're not around long enough to have sediment fall on top of them and that sediment harden and form rock. We also have periods of time where we can't find fossils. So like there's huge gaps. If you think of the fossil record as a timeline, there's huge gaps where we don't have that many fossils. And that was probably due to something like a catastrophic event, like a flood of some type, like the biblical flood of Noah and his ark. You know, that would have wiped out a whole bunch of creatures, and they would have biodegraded very quickly with no fossil left behind. Or, you know, a lot of people say that the dinosaurs became extinct because a meteor hit the earth. Well, when that meteor hit the earth, it created this huge amount of dust and ash flying up into the air, which then changed the dynamics of the earth. It would have caused like really dark, like darkness for a long period of time, which would have lowered the temperatures. At the same time, the plants would not be able to do photosynthesis, and the plants would die out, which would lead to this chain reaction. But with fossils, the fossil record isn't perfect, but we can use fossils as kind of a starting place. So most of our fossils are found in what's called sedimentary rock. Okay, if you think back to your earth science, you've got three types of rock. You've got igneous rock, metamorphic rock, and sedimentary rock. Sedimentary rock is basically things that settle. So over time, you get layer after layer after layer of dirt and sand. So it'd be like you lying on the ground and me putting blanket after blanket after blanket on top of you. Eventually it gets heavy and it starts to press. And it can press enough under the right temperature to actually harden and form rock. But when we look at fossils, what we're really trying to figure out is how old are these things, okay? And what can these things tell us? How can we compare these to other creatures? And so we look at what we call dating. Now, the first one's what we call relative dating. It's also called the law of superposition. But relative dating basically describes whether something is younger or older. It doesn't give me a date. Like, I don't know how old this is, but it just gives me an idea. Most of the fossils we find, in the ground. We have to dig down to them. And so it makes sense that the deeper down you go, the older something is. So when we look at relative dating, we're just kind of looking at the layers. Where do we find the layers? We're being like archaeologists. So it makes sense that the closer you are to the surface, the less amount of time you've been there. So the younger you are on the geological time scale. Now, again, there's exceptions to the rules. Mountains get pushed upward. You know that there's rock falls, you know that there's earthquakes that can, shake things and rocks fall down to the valley. And so just due to plate tectonics and earthquakes and natural disasters and natural occurrences, something from the top, which is really young, can fall down to the bottom where it should be really old. But again, that's exceptions to the rules. So like I mentioned with relative dating, it's what we also call the law of superposition. Super meaning above the position. So in an undisturbed rock layer, each layer is younger than the one underneath it because over time things have stacked on top of each other. But again, there's always an exception to the rule. For example, in this picture here, rocks from the very, very top could have over time, like with avalanches or earthquakes, fallen down to the bottom. But then at that point in time, we would have to compare rocks from the different layers and say, oh, wait, this rock is like this layer that's way up top. It must have fallen down. Relative dating cannot give us an age. It can simply give us an idea of this is older than this one. But sometimes we want to know, okay, how old is it? So when we want to know how old something really is, this is what we call absolute dating. So we can absolutely figure out how old it is. It's also called radiometric dating because it uses basically radiation. It's going to use something called a half-life to determine absolute ages. Basically, we have these things called isotopes. So let me give you a little chemistry lesson. One of the most common isotopes we talk about is carbon-14. Now, to be carbon has an atomic number of 6. That means it has 6 protons. To be carbon, you have to have 6 protons. Well, most of the time, if you have 6 protons, you also have 6 neutrons. And 6 plus 6 equals 12. That's its atomic mass. Well, 99% of all carbon in nature is what we call carbon-12. This is what we consider to be normal carbon. It has 6 protons, it has 6 neutrons. Well, there's things called isotopes in nature. Isotopes are atoms that don't have the correct number of neutrons in them. The most common isotope that we're going to talk about is called carbon-14. It's still carbon because it has 6 protons, but now it has 8 neutrons. Well, this is what we call an isotope. And carbon-14, think of it this way. Think of carbon-14 as seeing itself as an outsider. It doesn't feel normal. It wants to be normal. It wants to go to carbon-12. So what isotopes do is they decay. What that means is they break down. It's a lot more complicated than how I'm describing it, but this is a high school biology class, so just bear with me. But in the case of carbon-14, think of it as this carbon-14 wants to lose 2 neutrons. It wants to break down 2 neutrons. This is what it means when we say things decay. They are kind of breaking down in order to get to what we would call normal. So carbon-14 wants to be carbon-12. So it's going to break down, it's going to decay. Well, when things decay, they give off energy. So it's radioactive. A lot of times when we think of things being radioactive, we think of that as them being bad. Well, radioactive just simply means that it's giving off energy as it's breaking down. So we know carbon-14 is found in most organic material. Remember, organic means you have carbon. Carbon-14 is found in pretty much all living things. So we're going to do something called a half-life. A half-life is how much time it takes for half a sample to decay. What does that mean? let's say I have 100 M&Ms. And think of those M&Ms as being carbon-14. And I put them in a cup and I shake them and I just spray them across the table. Well, I can then eat every M&M that has the M side pointed up. And what's really cool is if you were to do this experiment at home, you would probably eat about half the M&Ms in that cup. So the ones that you eat are the ones that are back to normal. They're safe to eat. They have decayed. So we know how much time it takes for half a sample to go back to normal. This is what we call the half-life. So we look at this example here. Let's say we have 1,000 grams of an isotope, and we know it takes 500 years for half the sample to become safe to eat. Just think of it that way. Think of these as M&Ms. How much time, and these M&Ms are radioactive, how much time does it have to go by before they're safe to eat? So this is what we call the half-life. So as you can see here, if a sample contains 1,000 M&Ms, and we start at the beginning, okay, in 500 years, it will be safe to eat half of them. So that is one half-life. Then in another 500 years, another half have broken down. That's two half-lives. In another 500 years, another half have broken down. So this question says how many half-lives will pass before there's only 40 grams of this 1,000 grams left. So after 500 years, I have 500 radioactive particles left. After 1,000 years, I have 250 radioactive particles left. After 1,500 years, I have 125 radioactive particles left. After 2,000 years, I have 62.5 radioactive particles left. And after 2,500 years, I have approximately 31 radioactive particles. So it took 5 half-lives for me to get to 40 grams. Don't make a half-life harder than it is. It's the amount of time it takes for half the things to disappear. Think of it as you having a piece of paper. And I say tear it in half. And I time it. It took you so many seconds to tear that piece of paper in half. Then I tell you to tear half in half. And then I tell you to tear half of that in half. And how much time does it take to get to a certain point? Well, we can measure how much carbon-14 is in something, and using calculations, figure out how long this has kind of been sitting in the dirt based on half-lives, and we can figure out how old this particle is. This is just a graph that we can use to figure out half-lives. So let's just say we have the decay of cesium-137. So we've got time in years. So if I start with 100 of these cherries, think of them as cherries. I start with 100 of them. Okay. Well, half of 100 is 50. As you can see here, half of 100 is 50. Well, it took 50 years for me to go from 100 to 50. That's one half. So it looks like cesium has a half-life of about 50 years. You can kind of think of it that way. Again, it's a lot more complicated than this, but for our purposes, we're going to simplify it and it's going to make sense.